In this video, we'll be introducing the normal distribution. We have a number of learning objectives, knowing when it's a suitable model, knowing the notation, the shape, how much data, and being able to draw them. Now, if we have a look at the two graphs below, these are both histograms for the same data, but on the left, here, I've taken 128 pieces of data, and on the right, 256. And you can see that the more data I take, the more symmetrical in this case it is, and in this case it has a normal distribution, okay? A normal distribution curve, which we've looked at a bit, a bell curve. Now this is important continuous probability distribution, continuous data, and in this case it is normally distributed around the mean mu, which is in the middle. So I'll just draw a sketch of that. So you can see my red line is the sketch of the bell curve, with here my central value being my mean, which we call mu. This is a Greek letter that's often used to represent the mean, and it's just the letter M, mu. Now the normal distribution is not always a suitable model, but if it meets three criteria, then it is the suitable model, and these are the criteria that need to be met. So here's a sketch of the normal distribution, and it's really important that the data is continuous. It's not discrete, there's no gaps in between it, it is continuous data. Now if you have a look at this diagram, if this central line here was a mirror, then there is symmetry here and here. It's like it's been reflected here, and it's really important that this is true, that there is symmetry, and this line cuts it exactly in the middle. And in fact, it's in the shape of a bell, okay? Because it could be symmetrical and be like this, or like this, but it's really important it's like a bell. And lastly, let's talk about what this line here actually represents. We've already said it's mu, which is the mean. But in fact, if it is normally distributed, then all of the averages, so that's the mean, the median, and the mode, all about the same, they're all approximately equal, and they're all at the point of this symmetrical line. Okay, so that's basically what the normal distribution is, and we're going to discuss a bit about how we use it. But before we do that, just a quick note, we've been looking at skewness. Now obviously any distribution which is skewed is not normally distributed because it is not symmetrical about the mean, so it's very important that this is symmetrical. So if we have a look at this normally distributed curve, it's a bell shape and it's symmetrical around the mean, and it's continuous data. So this is a normal distribution. But what we also need to look at is standard deviations. Now remember, standard deviation is denoted by this letter here, which is little letter s sigma, and that is your standard deviation. That's how much it deviates standardly. So this distance here is one standard deviation, and that is as well. So this value here is the mean take away a standard deviation, and this here is a mean plus the standard deviation. And in fact, between these two here, we've looked at this vaguely before, there is 68% of all your values are between those two standard deviations, which means if you're going to look at it, each part here, because it's symmetrical, that's 34% of your values, and likewise here is also 34% of your values. Okay, but we go out again, so we've got another standard deviation here, so that's the mean plus 2 standard deviations, and likewise this side, that's another standard deviation, so that's the mean minus 2 standard deviations. And this time, that is 95% of the data. So here, all the way there, all of this, everything there, that is 95% of the data. And what that means is that between the mean and that standard deviation, so here, that is going to be half of 95%, which is 47.5%, and the other half would be the same. And then we will look at the last standard deviation. So we've got one more standard deviation here, which that's the mean minus 3 standard deviations, and this is the mean plus 3 standard deviations. And all the data between here and here, between here and here, so the whole of this, all of that data, well, it's a bit tricky this bit because there's an official value and the value that's found in the textbook for this course. So the official value for that is 99.7%, but unfortunately that's not the value they're giving you in this course. In this course they're giving you 97.8%. So for the purposes of this course, the percent there is 99.8%, which means that this half here is half of that, which is 49.9%. Now that all looks a little messy, so I'm going to show you a bit of a summary of that on the next screen. So here we are, here's a bit of a summary, and it's a bit clearer. So the first diagram is within 1 standard deviation, the second within 2 standard deviations, and the third within 3 standard deviations. Okay, here's a worked example. This worked example asks us on the same axes to sketch 2 normal distributions shown in the table. Now because they're normal distributions, they're going to have a bell curve, but they're going to be different widths. They could be low, they could be narrow, and that'll depend on the size of their standard deviations, because of course for each one we'll have the mean here, and then we'll have one standard deviation, another standard deviation, and the third. Now if I wanted to sketch it as long as it goes in each direction, it would actually go to minus infinity and infinity, so that's no good. So I just go to 3 standard deviations each way. So let's work out 3 standard deviations for A and 3 standard deviations for B. So for A, my 3 standard deviations is going to be 3 times 3, which is 9, and for B, 3 standard deviations would be 3 times 5, which is 15. So for A, my largest value is going to be my mean, 15, plus 3 standard deviations, which is 24, and my smallest will be 15 minus 9, which is 6. And likewise for B, it'll be 20 plus 15 and 20 minus 15. So that is going to be the width of my curves, and it also shows me the smallest number I need to have on my axes and the largest number I need to have on my axes. Let's give that a go. So let's look at curve A first. The mean is at 15, so that's here, and it goes up to 24 and down to 6. So it's going to look something like this, and that's curve A. Now before I draw curve B, I might be uncertain about how high to draw it. I know it goes between 5 and 35. I know its mean is at 20. But the area under both curves has to represent 100%, so it has to be representing the same number, the area underneath. So I can't draw them the same height. So this one is going to have to be lower. Okay, and that is because they're representing the same area. Now hopefully you can draw ones that look a little smoother than mine. It's quite hard on this app, but the idea of those two is that they're smooth, they're symmetrical around the mean, and they're representing the same area. Okay, we're now going to look at a second slightly longer worked example that we're going to work through. So here's our second worked example. We've got a long life light bulb and we've got to answer some questions on it. Now first of all, it has a mean of 12,000 hours and a standard deviation of 300 hours. The probability distribution we're going to be using is the one we're learning about this lesson, which is the normal distribution. Okay, so first of all, the normal distribution. But I can't just use that without assuming a couple of things. And it says to me, write one condition that I need. Well, there's a couple that I need. First of all, if we look back to our definition, it has to be continuous data. But also we have to assume that it's symmetrical about the mean. Okay, now we're going to look at some probabilities. Now what I highly recommend you do is draw yourself a curve, a normal distribution curve, to get a bit of an idea of this. So here's my sketch of my curve, and I'm going to put in all the data that I know. Well, I know the mean is 12,000, so I'm going to put that in. And then I also know the standard deviation is 300. What that means is the distance here is 300. So that's 12,300, that's 12,600, and that's 12,900. And likewise, it's 300 here, so that's 11,700, 11,400, and 11,100. So that is my curve. It's got all the information I need on it with my mean and my standard deviations. Now it's asking me what's the probability that it is between 11,400 and 12,600 hours. Well, that is 2 standard deviations each way, and I know from my rule that I hopefully have written down that between 2 standard deviations it is 95%. So this is going to be 95% of that data. So for B part 1, 95% of light bulbs last between 11,400 and 12,600 hours. Now what's the probability though that they last less than 11,400 hours? What's this probability down here? Well, if I think about it, the whole of this probability that I've just had, that's 95%, and that must mean everything else is 5%. So if those two sides are 5% and they're symmetrical, they must each be 2.5%, which means the probability that it is less than 11,400 is 2.5%. Okay, now let's look at part C. Part C says that 5,000 light bulbs are tested. Estimate how many of them would last longer than 12,600 hours. So let's have a little look back at that. So that's my question, and I want them longer than 12,600 hours. So I want them this side of the graph. Well, I've already said that that side is 2.5%. And if 5,000 are tested, I need to find 2.5% of the 5,000. And that will tell me how many light bulbs that is. So in my calculator, if I just use whatever method you usually use, whether that's 0.025 times 5,000 or any other method, you should have 12.5. So I would expect 12.5 light bulbs to last longer than 12,600 hours if I did a batch of 5,000. Okay, so using all that you've learnt in this video, have a go at the questions now.